So, today we are going to look at convergence conditions. We have seen convergence conditions before, but we did not see the full condition. So, we will today see that. Then we will see, I mean, what happens is that very often when you are trying to identify the system, even at that time the system might be operating in closed loop. So one thing we have found, that we have noted that if the system is operating in closed loop, then what tends to happen is that the data vector phi gets correlated with the noise, because the noise comes through y. If you are using feedback to determine u from y, then the same noise gets into the data vector, it gets correlated, and you might get some bias in the parameter estimate. And we have also seen that to get, and at least one step that you can take to get around that is to model the system in greater detail, using like extended least squares and things like that. But here we will see a new phenomenon which might happen if you are doing identification in a closed loop. So that we will see. I mean, structurally something changes if you have data in closed loop. And finally, before leaving least squares, we will look at some practical variants of least squares. Some things sometimes you have to do, some tricks you have to do to ensure to take care of certain conditions. They are very simple modifications which are intuitively clear as to why they are done. So we'll look at them. You will perhaps recall that we had noted that one of the conditions, we found that the parameter error theta minus theta naught was given as something like phi transpose phi inverse phi transpose v, where v is the noise. Such a condition came. So this is inverse. So we argued that first of all this has to be small. So for ensuring that this is small, we proposed several things like extended least squares, instrumental variables, which will make this thing small. And the second condition is that this, even if one thing is that ensuring this is small, but this cannot always be ensured to be 0. So the other thing to ensure is that this will continuously grow as n increases. The phi transpose phi inverse, these are capital Phi's, matrix will continuously grow in size. Now now what is this? So continuously grow means its size means it will gradually this phi transpose phi matrix will continuously grow, because if it continuously grows, then its inverse will continuously grow smaller. Now what is meant by phi transpose phi continuously growing? We mean that if we take any vector, it is the same thing, that this is supposed to be a positive semi-definite matrix being phi transpose phi. So we are, so that if you take any vector and compute phi transpose phi x, then this will continuously, this value for any x will continuously grow. That is what we mean. This will be a scalar. So what is phi transpose phi? Phi transpose phi is nothing but this sum. Here I have used small phi's that we have seen in class, that basically I mean phi, the capital phi actually consists of small phi's as rho. Each row is a small phi. Actually each row is a small phi transpose. So when you take phi transpose phi, then these rows will get, you will get this sum basically, because this is your capital phi transpose and this is your phi. Each one of them are small phi transposes. So you have phi 1 transpose, phi 2 transpose, phi 3 transpose, and so on. So what you are requiring now, it is well known that for any vector x, this value, this is a number for any vector x, and if you have any matrix x transpose, any matrix A, then x transpose Ax always lies between lambda mean norm of x square and lambda max norm of x square. This value will always lie between lambda mean and lambda max times of this x transpose x. In other words, if you multiply by a matrix, I mean a vector by a matrix, you are, what you are doing, you are turning it and you are stretching it. So the length of the resulting vector will always be between lambda mean and lambda max times this. That is a result. So if lambda mean, the minimum eigenvalue of this becomes infinity, then obviously the matrix for all x, this will become infinity. That is the idea. So the minimum eigenvalue should go to infinity. This is a statement. Now this is okay, this we have already studied, but now the question is that how do I ensure this? I have to ensure this. So how do I ensure this? I have to ensure this by two things. One is that I have to ensure this by, what does phi contain? Phi is a vector. So it contains firstly some input output values. Outputs are again generated by inputs. So I have to first ensure this by choosing my inputs, because that is an actionable item. I mean I can actually apply that input. If I want this to go to infinity, then what input should I apply? That is a question. That is a very concrete question which you should know. And second question is that the way these elements are arranged, that is yk minus 1, uk, whether there is uk minus 1, whether there is uk minus 2, that is the structure of this vector. That is also important. So the structure of the vector is important and the values are important. So the structure of the vector is actually selected by what? By the model structure. What A and what B you have chosen. From there comes the structure of phi, right? So this condition will finally translate to a condition on the model structure you have assumed and a condition on the input. If you can ensure these two things, then phi transpose phi will grow unbounded. So how do you ensure that? I am stating this without proof. There is a proof which is reasonably complicated even in the deterministic case. In the stochastic case it is extremely complicated. So we will not go into the proof, but we will remember the result, because the results are very important things for identification, very well known results. So the first result says that if you have chosen, let us take a model structure that is ay is equal to bu plus v. This model structure we are talking about, ARX. So, the first condition is that this A and B should be relatively prime. What does it mean? What is meant by relatively prime? We will see. The other thing is that is you must choose such a model structure such that there should not be any common factor. And if you take a system y and u which fits in this kind of a description, that is the data is generated in this manner where A is a polynomial, B is a polynomial, that is the data itself fits this description, and you have taken this model structure itself, you have taken this A and this B to estimate your parameters, then this A and this B should be relatively prime, that is they should not have any common factors. Any polynomial can be broken up into factors. So, A and B cannot have common factors. Why? We will see. There is a very intuitively clear reason. This condition is called parsimony of model structure. Actually, the word parsimony means something like simplicity. It means that, you know, if A and B becoming relatively prime means what? Means that the transfer function B by A cannot be reduced further. If they have common factor, then you can cancel it. So, if they have common factor, then this B by A can be further simplified by cancelling that factor. But if they do not have common factor, then it means that B by A cannot be simplified further. So, it is in their most simplified form. That is why it is called a parsimonious structure, right? Parsimony means simplicity. The second condition is that this condition also I mean actually it can be stated in time domain also, but I have deliberately stated the equivalent frequency domain condition because that makes more meaning. The time domain condition is basically a sum of, again, I mean something like this only, something like this only. So, it will not make, you will not know how to ensure that condition. So, the frequency domain condition says that the input has a spectral distribution, that is if you take its spectrum, it should be non-zero in at least at 2n number of points. What does it mean? In its two-sided spectrum. For example, if you take a sine wave, then a sine wave has how many non-zero points? 2. If you take a DC, it has how many non-zero points? Only 1. If you take 2 sine waves, it will be non-zero at 4 points, two-sided, plus minus omega. So, so basically this means that it should at least have n sine waves. If the order of A is n, if it is an n-dimensional nth order polynomial, then the input that you are exciting the system with must have at least n sinusoids of sufficient power. So, it should be, this is a rather theoretical, somewhat theoretical looking condition, so although it has a practical. Why? This also we will see. And such an input is called persistently exciting input of order n. Right. See, the idea is that if you are trying to know a system, you have to excite it. If you cannot excite it properly, if you do not excite all its modes, then you cannot identify it. So, you should be able to excite all the modes together in your input output data, all the modes should be there. So, to be able to excite all the modes of an n-dimensional system, because this order is n, you need n sinusoids. So, whatever input you give, that must be decomposable as a sum of n sinusoids of non-trivial power. Only then, if you ensure these two conditions, there is also a condition of stability or boundedness of data, but that we are not considering because in practical situation all data are bounded. That's a somewhat theoretical condition. Now let us see a little bit as to why these conditions arise. Okay. The first thing is what I have said, that if AQ inverse and BQ inverse has common factors, actually what are we doing by specifying what is the identification? Identification says that it first specifies a structure of A and B. So you say that it is equal to A naught plus A1 Q inverse, etc. And similarly it specifies a structure of BQ inverse, and in that structure it now looks for parameters. So this, what is the model? See, the model is, see, the same system can be parameterized in various structures, right? For example, any first order system which is 1 minus AQ inverse by 1 minus BQ inverse, this is a first order system, we say first order. It can also be written like this. So it can always be seen as a second order system. See, these two, if you really break it up, then the forms will look different. But actually for arbitrary value of ABCD, this system is the same as this system, correct? So a model is the system itself in whatever way it is parameterized. So actually these two systems are same, but their parameterizations are different. Now if we want to find the parameters, then we should take a parameterization which is unique, which means that if two systems are equal, it will imply that they have the same parameters. This condition should be satisfied. Otherwise data is generated. Now if you have several kinds of parameterization, all of which will make the same system, then from that data which parameter will be the solution? There will be non-unique solutions to the identification problem. So first of all you have to ensure that there is a unique solution to the identification problem. In other words, if you have generated the data is generated using model. The data if you feed u and y to this, and if you feed u and y to this, you will get the same u and y. So if data is generated from the same model, from one model, it will imply that in that model structure there should not exist any other parameter which will give rise to that data. That parameter set should be unique. But if A and B have a common factor, then that parameterization is not unique, because this is a parameterization, this is a parameterization. What have I done? Here I have multiplied by 1 minus CQ inverse, here I have multiplied by 1 minus DQ inverse. So in this model structure, this parameter and this parameter value are going to be different if you really multiply, but they are the same system. So if you feed data, if you are given a pair of input output data, there is no way of determining which one of these parameters is the right one, because both are right ones. So the parameter search is not unique.
So but when we get a solution, we get value of D, and then we will come to know that obviously these are common factors.
Right, but the thing is that you see, but how do you know that you will even come to a unique solution? We are trying to find the condition such that there will be a unique solution. But in this case there does not exist any unique solution, which means that there may be input output pairs for which it will give different solutions, right? So that is without really getting into the proof, we are trying to understand the rationale behind it. So first of all, this is needed to make the problem non-unique, and we will see that this thing comes again and again. Even in the case of identification in closed loop, again we will encounter a situation where this parameterization will become non-unique. So first of all, the parameterization should be unique, such that there exists only one solution to that which fits the input output data under that structure of the model. So that is the first thing. For example, now the second thing, why there should be n unknowns, why there should be n sinusoids. Basic idea is, let us say consider a first order system. How many unknowns? A and B, 2 unknowns. So we must, when we excite, suppose you are given a box, and you are told and you are given a sinusoidal signal generator, and you are told that this is a first order system, so please identify. You are given a CRO, no computer, nothing. What will you do? You will apply a sine wave. So input sine wave you know, output sine wave you know. You will first measure the gain difference, 1 volt, whether it becomes half volt or quarter volt, and then you will see the phase difference by feeding to a double channel CRO. So you will see how much phase shift has occurred from the input. So you are basically making two measurements. One is the amplitude gain, and that is the phase. So you have, now you will try to fit it. So you will find a formula in terms of A and B of the gain, and a formula in terms of A and B of the phase. So you have two equations and you have two unknowns, so you will solve. That is how you will get A and B. So if you excite with one sinusoid, a first order system, you get enough number of equations such that you can solve it. If you excite it with DC, will you be able to solve it? You will get only one equation and you have two unknowns, so you cannot solve it. So this itself shows that if you have, similarly you can find that if you have a second order system, you will require two, because you have two poles. So if you have two poles, you need two sinusoids to excite them, right? So this is also intuitively very clear. It can be proved in a very rigorous manner using huge mathematics. But the basic idea is that this also applies to a person. If you really want to know, I mean, you have to interact with it properly. If you really want to know what sort of a person he is, without interacting, if you are always speaking of cricket, you cannot know whether he has an interest in literature. So it's like that. So this is, but remember that these two are very, very well known conditions for any identification, that the model structure should be simple enough. It should not be over parameterized, because if it is over parameterized, then you will encounter this non-uniqueness of solution problem. On the other hand, if it is and you should choose, when you are, after all, where from have you got the identification data? You must have got it from some experiment. You want to identify the model, so you must have arranged for some experiment, arranged for collecting some data. So when you are arranging for that experiment, you have to have at least some knowledge, and then you have to select your inputs properly so that you have excited all the modes of the input. If you have not excited something, you will not get that. Now let us look at identification in closed loop. So this is our closed loop situation, right? For the time being, let R is equal to 0. There is no reference in. This happens. There are some control loops for which the control is, the set point is 0. One example I know of with which I am involved is the roll loop of any aerospace vehicle. There the set point is always 0 because you don't want it to roll. You might want your vehicle to go up, to go out, to go down, this way, that way, but you generally do not want your vehicle to roll. So your roll control set point is always 0. You want a 0 roll angle all the time. So that is such a loop. There may be other loop. For example, when you are having a linearized control, then you are always writing the control loop in terms of incremental variables. So if you are writing it in terms of incremental variables, then also your set point is 0. You want the increment from the operating point to be 0. So your set point is 0. So it is not a very uncommon situation, though having a non-zero set point is also common. But if R is equal to 0, then something very interesting happens. What is that? If you have this to be 0, then it turns out that between U and Y there exist actually two relations. Both of them are correct. Y is equal to GU and U is equal to HY. So if you identify between U and Y, what you do in identification, which one will you get? Both are correct. So there is a possible potential non-uniqueness solution. you are very likely to get a situation where this solution is going to be non-unique. Why? You will, for example, if you take this system, simple first order system, this is U, this is my G. So simple first order plant G, and assume that you have taken a simple proportional feedback, UK equal to minus KYK. Then obviously UK plus KYK equal to 0. So this equation you can always add any amount of this term, that equation is also satisfied. This lambda can be arbitrary because UK plus KYK is always 0. So this equation is also true. So if you break up, you will get, so the open loop plant satisfies this equation for arbitrary values of lambda. And not only that, worrying part is that even if you know K, even if you know the feedback law, you cannot solve out because this lambda is arbitrary. You don't know what lambda is, it can be anything. So you will never get, this is a typical case where there is multiple parameterization, I mean non-unique parameterization in the presence of feedback, right? Now why does it happen? Because this law is actually simpler than this law. So the data simultaneously satisfies this also, but you are trying to identify the data using a higher order model. You have taken a data which actually satisfies a simpler model, but you are trying to identify it using a higher order model. That is the reason. So what are you going to do? So you can do several things. For example, if this does not happen, if R is not equal to 0. Because if R is not equal to 0, then this model structure, if you put, suppose you had R, then you will have an R here, and you will have an R here. If you substitute, you will get a minus lambda R, correct? So if you are, now if you identify using, you are identifying, what is your identification? Your identification is using this model structure. So you are trying to fit the data using in this form, but when you have a lambda R term, obviously this does not fit this model structure, so it is unique. This data will satisfy this model structure only for lambda equal to 0. Otherwise no other model, I mean especially if R is persistently exciting and all, then this data, the data which actually satisfies this can be identified using this structure only if lambda equal to 0 for no other value. So you will get the right parameters. Similarly, you could also do another thing. You could choose a higher order feedback, not only minus k yk, also minus L yk minus 1. If you chose that, and now if you substituted the same thing, then here you would have got a minus lambda L, can't write, yk minus 1. So now your model structure would have been second order, that is the A polynomial order would have been second. So the data really satisfies a second order parameter thing if lambda is non-zero, but you are trying to identify with a first order model. So that will be satisfied only if lambda equal to 0, not otherwise. So therefore you again have unique parameterization. So this shows that there is potential danger of getting non-unique solutions in closed loop identification, especially when either the reference input is not significant and the control law is too simple. In such situations you have a potential problem. So the idea is that, so what you are practically going to do is that you probably cannot do much on the control law because it may be already existing, but you have to have a decent amount of reference input which is significantly varying while you are doing the experiment. So how do we identify? If you ensure that, then there is no problem. And then, so closed loop identification has two problems. One problem is that generally the error will tend to get correlated with the data vector. That's one problem. That will give you some parameter errors. That problem you can solve by either choosing those various mechanisms like having a longer model structure or having an instrumental variable. You have to solve that problem if the data vector tends to be correlated with the noise. On the other hand, it might lead to some structural problem in the sense that the parameterization itself may become non-unique. If that happens, then you have to, the most common solution is to have a significant and persistently exciting reference input. If you have these two, you will get a decent parameter even when the system is operating in closed loop. So, all systems cannot be operated in open loop. Firstly, if you go to a plant, suppose you go to a factory and say, please let me open that blast furnace loop, I want to identify it, people will throw you out. Because all plants, there are plants which cannot be operated in open loop. Nobody will allow you. So you have to operate it in closed loop. You might request the operator to give some set point perturbations so that you can collect your data. You cannot do more than that. So, so in such a case, you will be forced to identify the plant in closed loop. So there are two approaches. One approach is, now you do not know whether if you want to do a kind of identification based on U and Y, then you first have to get U. That depends on again that depends on whether you have the transducer structures for it. Y is generally measurable because after all, if the operator has to control Y, he has to see it. So that value will be generally available in the control room. Command he himself is giving, generally available. But whether the plant finally the input that it gets may be in the form of some exotic variable like a very high current or maybe some fluid flow, that may or may not be measurable. It may be measurable in the field, it may not be transduced to the, you may have so many practical difficulties. So there may be situations where getting U and Y for identifying a model may not be so simple. In such a case, what you have to do is you identify a model between R and Y, reference input and Y's. So if you do that, what will you get? You will get the closed loop model. For why are you so if you know the controller, if you already know the controller beforehand, because it will be there in some manual written. After all, some company came and set up that controller. Usually it's a digital controller. So if you know the controller and if you have identified the closed loop plant, then you can solve out the open loop plant. Just numerical solving, right? So that is possible. So this kind of identification is called indirect identification. Direct identification is where you directly identify the plant taking its inputs and outputs. Indirect identification is when you identify the closed loop plant and solve out the open loop plant, right? So this now we more or less have covered most aspects of least squares. Least square is a huge area. 200 years of research on least square started from Gauss. So enormous amounts of results, but anyway, we have more or less in the context of identification we have we have at least touched upon most points. So now just before leaving, we'll look at certain practical variations to the basic least square algorithm that you can do. Sometimes you need to do them. There could be various situations. We already, I mean, sort of got a taste of that. We had seen the exponential data weighting case, where we wanted to weigh in the least square criterion, we wanted to give different errors different weights. Then we had also seen the instrumental variable algorithm, which also leads to the least square. Only thing is, in some cases phi gets substituted by another vector called the instrumental variable vector. In this case, we will also see some case. For example, there may be some situations where you don't want to update your data based on at each data point. Why? Why could that happen? One reason is that you have modeled your noise, that okay, generally noise is, for example, suppose it so happens that you know that the data is noise. Suppose when you have tested the data, you found that the data generally white type of data, noise, variance some 0.1 volts. Now, so I mean, some weird things may happen. It may be a plant where sometimes maybe when you took the data, there is some arc furnace running around, or there may be some welding done. When such things do, I mean, take place, because there is a very high current flowing in each one of them, either in electric arc welding or in arc furnaces or in very large motors, you get a very high amount of electromagnetic interference suddenly coming. So what I want to say is that there may be situations in the data where for some short periods the normal property of the data is disturbed. So you get some samples which are for some reason very erroneous. Such data are called outliers. They do not conform to your normal model of the data. Now the point is that you have to be very careful about the outliers. Why? Because one outlier coming, suppose your parameter was nicely converging, it has come to the true parameter and it is holding, it is slightly oscillating around the true parameter. Suddenly if one or two outlier data points comes, it will create so much of prediction error, y minus phi transpose theta, that immediately your parameter estimates will get a jerk. They will just simply go away, because those two data points, for some reason you got some bad data. You should never update your model using bad data. So you have to build when you practically build a least square algorithm, you have to build in protections against these things. So one way of protecting could be outlier rejection, that if you know that if your parameters have more or less converged, you cannot get more than this error if you have good data. So if your prediction error suddenly goes beyond some really I mean, you can be conservative in your estimate, but if it goes even beyond that, then you don't update on that. You simply assume that this data has come due to some bad reason. I mean, this is not normal data, so I will not update. So then you can say that I will set this ak equal to 0 in this equation if the error is greater than epsilon 1. You just set some limit that this is bad data, I am not going to update my parameters on that, it will pass. Then what will happen is that simply theta k plus 1 will remain as theta k, and similarly pk plus 1 will remain as pk. You are just automatically picking out one data point and throwing it away. Similarly, there may be sometimes you also want to incorporate what is known as a dead zone. In some cases, see, it is not good that all the time you may not like to estimate, I mean keep on estimating all the time. So if you, for example, you may know that I have a noise of 0.1 volt coming. There is a white type of noise of 0.1 volt standard deviation. If you already are aware of this, and if your prediction error is giving you a prediction error of 0.02, then why should you update the parameter? Even in the face of the noise, your parameter has sufficiently accurately predicted the output. That much of 0.02 volt is coming because there is a much larger noise. So as long as your prediction error is within the noise limit, actually your parameter is satisfactory. That noise will come anyway. That prediction error you cannot reduce because of the presence of the noise. So then you should not update again. So you should not update unnecessarily all the time. So in such a case also you might like a selective data weighting, set ak equal to 0 if the error, prediction error falls below a certain limit. Such things may happen. So this you may like to build in this selective data weighting, which will give you an inherent protection. Suddenly your parameters will not go away. See, these things are very dangerous. I mean especially these things were employed when people started working on adaptive control. Especially in the process control industry, people tried online estimating the parameter, online designing the controller, and then applying the controller. So if your parameter suddenly gets a shock, then your controller suddenly gets a shock. I mean you will get an absurd controller. So for some time suddenly your product, suppose you are controlling some strip width or some wet paper tension. If your controller suddenly changes, then you are going to apply, I mean, meaningless input for a little while at least. So during that time it might jeopardize your operation. So that's why people do not want such things to happen. Better not change the controller during that time. Let it continue. After all, how much it could have drifted away within one sample. The other thing is covariance modification. See, sometimes actually what happens, actually it is the covariance is the gain of the least square estimator. So if the covariance goes to 0, then what happens is that the estimator gain goes to 0. Now it may happen that because covariance is what? Covariance is phi transpose phi inverse, roughly speaking, not roughly speaking, exactly speaking. So that obviously goes to 0. So now the problem is that suppose you are having a case where the parameters are, parameters typically change with what set point? The linear model parameters of a boiler which is operating at 50% load are different from a parameter from the parameters of a boiler when it is operating at 100% load. So and the operator changes the operating point from time to time, maybe over 2, 3, 4, 5 times in a day. If you take a power plant boiler, right in the morning till about 8 o'clock it will have a low set point. At 8 o'clock everybody will start going to office, so the load will increase, everything will start. So at that time he will increase the boiler setting to maybe initially 50%, then maybe at 10 o'clock he'll make it to 100%. Again at 3 o'clock or it may be lower. Again during evening he will make it higher. So he continuously changes his operating point, not too frequently but at least 5-6 times in a day. So at each of those points the linear model changes. So suppose you are running an online estimator. So what you are going to have is that the parameters have converged and your covariance has died. It will die. Now suddenly the operator has changed his operating point. Now the model does not fit. The model does not fit, so there is some error generated, but your covariance is gone. So though the error is crying change parameter, there is no strength in the covariance to push the parameter to the new value. So if you expect parameter change, then you should always keep your covariance live, at least at those instances, because if the covariance is not live, it is not going to push the parameter, it is the gain. So that is why in fact you can see that in exponential data weighting we do precisely the same thing, because there we are expecting a time varying parameter, we keep the covariance from dying. So the covariance will not die because there is the 1 by lambda factor in the covariance update and lambda is less than 1. So in each update we are giving it a little boost So it does not go to 0. So that's what we do in time varying parameters. Every instant we give a boost, or sometimes when we expect set point, that is if the prediction error goes beyond a certain value, and maybe if it stays for 2-3 instants, if it goes up just for one value, it might be an outlier. But if it stays, that means your model is consistently bad. For 5 samples you are getting large prediction error, which means that the parameters need to be changed. At least you need to retune your estimator, boost the covariance, again set it to some may not be exactly like an initial value, but give it a strong value, right? So this is also required very much. If you don't do it, then after some time you will not be able to, it will take a long time for the parameter to track. Third thing is, how do we incorporate? If we know something about the process, we must incorporate it in our parameter estimator. If we know that the process has a positive DC gain, we should have an estimator which all forces that the DC gain is positive. Now, how will you get DC gain? For example, AQ inverse, suppose your supported model is BQ inverse by 1 minus AQ inverse. What is the DC gain? B by 1 minus A. So you might say things like B by 1 minus A should be positive. That you could have such conditions. You could have conditions, you know that the system is stable. So at any condition, if you find that you are getting such an AQ inverse which has unstable poles, obviously it is not correct. That is your a priori knowledge. You could say that this parameter cannot go beyond this limit. Such knowledge may exist. So in which case you have to in that case you have to have not only just least square optimization but plus constraint satisfaction. So at every instant with the parameter that you get, you have to inspect whether it satisfies the constraints. If it does not satisfy the constraint, if directly the parameter which is given by least square does not satisfy the constraint, then you have to find the closest parameter to that which satisfies it, and that is achieved by what is known as projection. So you have a part of the parameter space which will satisfy the constraint. So you have a part of the parameter space overall, suppose this is theta 1 theta 2 parameter space, 2 dimensional, just assuming, and suppose you have given a constraint that this is the feasible part. So every time, suppose if you get something here, then you have to find the closest parameter which falls in the region. Why closest? Because otherwise, after all, how did you get this parameter? You got this parameter by LSE optimization. So it leads to low prediction error. That's how you got it. So you must maintain low prediction error as well as satisfy this constraint, right? So that's about all. Two little things. Firstly, we didn't talk about multivariable. That is very simple. Actually, for a multivariable system, your parameter estimation equation will become like this. This is UI. So rather than having AQ inverse Y is equal to BQ inverse U, you will have a number of B's. There is nothing very unusual. So the multivariable identification can be done exactly in the same manner. Sorry. And this is the common denominator. That is, if you have B1 by 1 minus A1 Q inverse U1 plus B2 by 1 minus A2 Q inverse U2 Y is equal to, then you have to take common denominator. So your A will become 1 minus A1 Q inverse into 1 minus A2 Q inverse, and your B1 will become this B will become B1 into 1 minus A1 Q inverse. Note that in that case, this and this will have a common pole. Yes, it will have. But all these parameters, that is capital B1, capital B2 and A, will not have one common factor. Between B1 and A there will be a common factor, between B2 and A there will be a different common factor, between B3 and A there will be another common factor. It will not happen that B1, B2, B3 and A all have one common factor. That will not happen. Because between B1 and A the common factor is 1 minus A1, between B2 and A the common factor is 1 minus A2. Right? So the for multivariable, that is the condition, that all of them should not have a common factor. So that's simple. All I wanted to say without going into it is that the multivariable case is nearly similar. Third thing is, last thing is, oh, maybe I should stop because there is somebody waiting here. So just wanted to say that there may be situations where you want to focus your estimator towards certain frequency bands. You want to know the low frequency properties very well. Don't care so much about high frequency properties. In such a case, the idea is that you have to apply input which is rich in low frequency. You cannot give a high frequency input and then expect good accuracy in your low frequency model. And to improve that further, you should use a filter which will further focus the input output onto the frequency band. So if you do that, then on that focused frequency band you will get good accuracy compared to other bands. So that is all for today. Thank you very much.